We're going to talk about differentiability. So, what does it mean for a function to be differentiable? We've seen that word before in other examples. Something is differentiable if the derivative exists for every value in the function's domain. So a definition that we have written here is that a function f is differentiable at a, so at a particular point, if f prime of a exists. So if the derivative at a exists. It's differentiable on an open interval if it is differentiable at every number within the interval. So we want to know, is the function f of x equals the absolute value of x differentiable? So thinking about what type of function this is, it's an absolute value function, and we know that when we're trying to figure out the derivative or the slope, that we can use limits. So we need to think about this as two pieces, because an absolute value function, what's inside the absolute value can be positive or negative. So the first thing we're going to do is we're going to look at when x is greater than 0, and that would be on the interval from 0 to infinity. So I want to find the derivative, so f prime of x, okay, on this interval. So what we're going to do is use the limit definition of the derivative. So I'm going to use the f of x plus h minus f of x over h one. So I'm going to write that out. So I have the limit as h approaches 0 of the absolute value of x plus h minus the absolute value of x over h. Since I am on the interval from 0 to infinity, and I know that my numbers are going to be positive, what I'm going to do is drop my absolute value bars and make everything the positive case. So we're going to say the limit as h approaches 0 of x plus h minus x over h. And these x's are going to cancel out. So I have the limit as h approaches 0 of h over h. And I can simplify this. I don't want to plug in 0 yet. If I plug in 0, I'm going to get 0 over 0, which is an indeterminate form. So remember, we always want to make sure we don't get 0 on the bottom. So I'm going to simplify this by using algebra and get 1. So now if I plug in 0 into here, I end up with just 1. So since I have an answer and I got 1, that means that on this interval, so we'll say therefore f is differentiable on this interval, so for any x greater than 0. So for any x value that's greater than 0 that's on this interval, that piece of the graph is differentiable, right? It has a derivative, which is 1. Now we got to consider the other side. So I'm going to do the same thing. I'm going to say it's the limit as h approaches 0, but here we want to find out when when x is less than 0, so on the interval from negative infinity to 0. So I'm going to use the same setup here. So if I'm trying to find the derivative here, I'm going to have, again, the absolute value of x plus h minus the absolute value of x over h. Because it's where x is less than 0, I'm going to assume that what's inside the absolute value bars is negative. So I'm just going to rewrite this as negative x plus h minus negative x over h. So everything's getting negated here. So when I do this, I can distribute my negative, and I end up with negative x minus h plus x over h. So similar to the other piece of this, we have the x's are going to cancel out. So I have the limit as h approaches 0 of negative h over h. And just like before, we don't want to plug in 0 since we're going to get 0 on the bottom. So I'm going to use algebra and simplify this. Oops. And I get negative 1. So when I plug in 0, I get negative 1. So again, we do get an answer. We get negative 1 as our limit, which is our derivative. So we're going to say, therefore, f is differentiable for any x less than 0. All right, so we were able to see from both the positive and negative pieces of this that f is differentiable when it's greater than 0 and when it's less than 0. But what happens when it's exactly equal to 0? So if I want to figure out when it's exactly equal to 0, I'm doing the derivative at a point. So I'm finding f prime of 0, which means I can use my limit definition of the derivative, but instead of x, I'm going to plug in my point, which is 0. So that's going to be like my a value. So I'm going to do the function at 0 plus h minus the function at 0 over h. So I have the limit as h approaches 0 of the absolute value of 0 plus h minus the absolute value of 0 over h. So if I simplify this, I end up with the limit as h approaches 0 of the absolute value of h over h. Now, I can't plug 0 into here because I have 0 in the bottom. And notice that I still have absolute value here. So what I need to do is I need to break this up into the right-hand limit and the left-hand limit. So I'm going to, let me change colors. So we're going to do the limit as h approaches 0, we'll say from the right. If it's coming from the right-hand side, the absolute value, whatever's inside, will be positive. So this is going to be h over h. And if I simplify that, I get the limit as h approaches 0 from the right of 1, which is 1. I have to do it from the other side. So I'm going to do the limit as h approaches 0 from the left. So that means that my absolute value, what's inside, is going to be negative. So I have negative h over h. So I get the limit as h approaches 0 from the left of negative 1. So when I plug that in, I get negative 1. Okay, so when it's greater than 0, it was 1. When it's less than 0, it's negative 1. But at 0, we have those conflicting values. One is 1 and one is negative 1. So since the limits are different, f prime of 0 does not exist. Thus, f is differentiable at all x values except for 0. So overall, f of x is not differentiable because of that 1 point at 0, because we couldn't find the limit since the left and right-hand limits were not the same. So if we wanted to write a formula for the derivative of the absolute value would be 1 if x is greater than 0, which is what we found using the limit, and negative 1 if x is less than 0. And then the graph corresponds to the equations. So the fact that f prime of 0 does not exist is reflected geometrically in the fact that the curve y equals absolute value of x does not have a tangent line at 0, 0. So when you're at 0, 0, because the slope from the right and the slope from the left are different, so if we look, we can see that here we have a negative slope, here we have a positive slope. When they're approaching the same point of 0, they don't have the same slope, like they're completely different signs. And there is no horizontal tangent line here because it's forming a point. It's not like a flat piece. So overall, this is not going to be differentiable. Another important piece about differentiability is that if f is differentiable at a, so at a particular point, then f is continuous at a. Okay, so if something is differentiable at a point, it is also continuous at that point. But you want to be careful because the converse of that is not true. So if a function is continuous, it does not mean that it's differentiable. Okay, so again, just to kind of repeat myself, if something is differentiable at a point, it is also continuous. However, if something is continuous, it doesn't mean that it's differentiable. And we're going to look at examples of that. So how can a function fail to be differentiable? Okay, there's 3 main reasons. Okay, 1, if the graph of a function f has a corner or a kink in it, then the graph of f has no tangent at this point, and f is not differentiable there. So that is similar to the value, the absolute value one that we saw before. And we'll look at that in a minute. So in trying to compute f prime of a, we find that the left and right limits are different. So that's the example we just did. If the graph of a function f has a point of discontinuity, so a jump discontinuity, f fails to be differentiable. And then if the graph of a function f has a vertical tangent line when x equals a, then f is continuous, but the limit is going to approach either like infinity or negative infinity. So it means that the tangent lines become steeper and steeper as x approaches a. So basically, the slope would be undefined. So if you have a slope that's undefined, it's not differentiable. So to kind of illustrate this a little bit easier, hopefully, here are the 3 scenarios. Okay, so examples of the 3 possibilities when a function fails to be differentiable. Okay, we have the first one, which is when you have a corner. So anytime that you have a point, you could call it a pointy point, any type of like corner, kink, point, when it kind of makes that V shape is not differentiable because at that point we don't have a horizontal tangent line. Or we don't have a tangent line, sorry. At the second one, where you have a discontinuity, we can see there's a jump discontinuity. So the limit from the left and the limit from the right are going to be different. And then in C, a vertical tangent, again, that's tangent line would be undefined. So since you don't have a defined tangent line, you don't have a derivative at that point. Okay, so then we're just going to look at each individual case again, just to make sure we understand. So here's an example. Okay, so does the limit exist at 0? So if I look at 0, does the limit exist? So is my limit from the left and the limit from the right equaling the same value? And in this case, yes, it is. And you can see that it's 0. Is y continuous at 0? So can I draw this without picking my pencil off the paper? I sure can. So is it continuous? Yes. Is y differentiable at 0, right? So in this case, it is continuous. Great. Does that mean it's differentiable? Not necessarily. So let's look at 0 and what's happening. Here we have a vertical tangent line because it's pretty much like a straight line there. So since we have a vertical tangent line, it is not differentiable. So I'm just going to put no, and I'm just going to write that it's a vertical tangent line. So a vertical tangent line means that we have a slope that's undefined. So even though this is continuous, it's not differentiable. In the second example, okay, we have again a graph, okay, and we want to know, does the limit exist at 0? So when I look at this, the limit from the left is infinity, the limit from the right is infinity. So does the limit exist? Sure does. Yes, and it is infinity. Is f of x continuous at x equals 0? So here's where 0 is. No, it's not continuous because you have to pick your pencil off the paper to keep drawing it. So no, it's not continuous. Is f of x differentiable at 0? No, it's not differentiable because we have a discontinuity. Right, we have that jump discontinuity, so it is not differentiable. Okay, and the last example. Okay, does the limit exist at a? So as I go from the left and I go from the right, does the limit exist? Yes, it does. Is it continuous at a? Yes, I can draw this without picking my pencil off the paper. Is it differentiable at a? Right, and if you notice, it makes that point. So is it differentiable? No. And that's because there's no tangent line. And it's like a corner. So you can, make note that it's a corner. It's one of those points. So we do not have this function being differentiable at